Now let's move on to the core part of this session, which is stacking. First of all, the objective of stacking is to generate a seismic trace just at zero offset, right? Artificially generated by processing. The processing is done by an MO correction. So you have this curve here. Assume this curve is approximately a hyperbolic curve, and based on the hyperbolic equation, you do the velocity analysis, and then based on this equation, you find the delta t, and then you do the correction. You shift this upwards, get flat, and then finally stack them. So basically, two things here. The purposes is to generate a zero offset. The tools is an MO correction. The theory is based on the hyperbolic equation. Why we do need a stack? So we need to see any beneficial we'll get from a stack. So stack, the signal will enhanced because they have a coherency along the curve. So, right? So the coherent event will be enhanced. Provide your velocity, NMO velocity is correct. Provide your curve, assume the curve perfectly fits the reflection. Right? By stacking, the noise will be somehow reduced. The noise includes random noise and the coherent noise. Right? Let's see random noise. Random noise means when you do the stacking, they are not coherent. Because they are not coherent after stack, they will somehow cancel each other, but not completely canceled. We'll see. Right? So the formula here, if your seismic trace consists of a signal and a noise, I means the I's traces, right? So some of them, the signal, because this is coherent, the signal will be untouched. You can see that one will be untouched, but the noise will be suppressed because this one will reduced. And how reduce? What sort of quantity we have? Let's see the next one. That's actually derived by one of the famous physician, Einstein. So you see, seismic science related to the very advanced physics. Einstein developed this. If we have a signal means you have the same direction, next signal, you can see they enhance, right? But for noise, you have magnitude, we call it error. But if it's random, means different direction. Next one here, randomly, right? You can see. So N of this end up, the final point is not exactly in the blue point. If in the blue means your noise becomes zero after stacking, but it's not. So where is it? It's red here, from here to here, right? So noise not enhanced, but somehow canceled. The final result will be square root of, right? Error is a noise magnitude. So forget about magnitude error. And here, right, remember in the previous slides, I said signal, N signal, summed together becomes the N signal, right? And divide by N becomes signal. But the N noise summed together becomes square root of N. Square root of N divided by N, you end up 1 over square root of N. You see that? So magnitude of noise will be reduced to 1 over square root n. Yeah. After stacking, your noise, n noise becomes n noise divided by n. You normalize back, right? You end up signal becomes signal. But noise here is the square root of n and divide by n. So you end up 1 over n. This is the capital error, right, in the previous slide. So random noise is reduced by an order of a square root of n, by a factor of square root of n. You can see stacking is a very powerful tool for suppressed random noise. Stacking also helps us to suppress some coherent noise. One example we showed before for the multilayer, for the water layer multiples, if we use a true velocity of subsurface reflection, and the multiples will be undercorrected, right? So when you do the horizontal stack, this outfaced curve will be, the energy along the outfaced curve will be cancelled partially, right? So that's also helps. So for coherent noise, it's usually generated by related shorts, right? Like a water layer multiple generated because of generated by the source, right? Like in the land seismic, ground roll also related to source. So it's generated usually by a source, but I also have some scattering, right? It's not 100%, also have scattering. You have a strong anomaly in the subsurface, it's general linear scatters. And coherent noise has a different move out to signal. This example I showed you before, because the move out for that travel time, the move out for refraction related to the subsurface velocity, but the move out of related to the water layer velocity, you see that? So they have a different move out, right? And after NMO, coherent noise, you have a residual move out, so that's undercorrected. So stacking is will reduce coherent noise. Stacking is a multi-channel processing because we sum all the traces together. It's called multi-channel processing. And the previous session last week, we learned the multi-channel filter. So stacking is a form of filter. What a filter is? Filter means we multiply each individual sample by a weighting coefficient, right? So in this sense, that's a multi-channel filter, right? Now let's see how stacking can reduce the coherent noise. That's a primary source receiver, water layer, reflection here, and the first order multiple. Basically, your wave bouncing within the water layer twice, right? And then in your seismic CMP gate or in seismic section, this apparently looks like you have a apparent reflection from here, reflection at here. And if we ignore the horizontal distance, right? We're talking about 1D here. So the travel time from here to here and the travel time from here to here, they are identical, right? So it depends on the, not depends on the velocity at this depth, but it depends on the velocity within the water layer. You can see that. So this is why they can separate from true reflection, primary reflection, and the multiples can be separated from true reflections. So multiple looks like primary, but has a different velocity. In this case, water layer velocity, right? And the velocity is lower than primary, So if it's higher velocity for the correction, for the reflection, that means your multiples looks like undercorrected, right? The velocity high. That was first order. No, second order, you have one more bouncing with a layer, within the water layer. And in your section, you will see, looks like you have another refraction. Again, this looks like a priming at a later time, but velocity is a water layer velocity because you do the velocity analysis, and then you can see this velocity actually is a water layer velocity. Okay, again, the velocity is lower than the priming, so that means in your stack section or in your CMP getter, CME corrector section, you can see this one. This one is under corrected, right? Velocity is too high because actual velocity used for this layer is higher than the water layer velocity. You see that? For pixels, that's a source receiver, that's a primary, but the first order pixel that's in the receiver side, source side, the same thing. Multiple looks like a primary because this one underneath, but Young velocity is RMS velocity. It's a RMS velocity of water layer and this velocity. You can see still the velocity is smaller than refraction. Okay, so for the pixels multiple, the velocity is not exactly the water layer. That's actually it is the average of here and here based on the RMS. Nevertheless, the first order pixels have a velocity smaller than the primary because this part velocity is smaller than the average velocity here, right? That's the short side pixels, same thing as the receiver side, if subsurface is flat, right? The second order, similar thing. Pole looks like a priming, but the velocity now is even smaller because now it's a RMS of this velocity, and this velocity. Just look like you have 3 layers, right? RMS velocity, remember, it's a mathematical derivation of a 3 layers velocity now, 3 interval velocities. Nevertheless, this velocity of apparent refraction, which is pixel multiples, is smaller than the primary at the steps. In the short side, pixels almost same. Why is it almost? Because there's something here, just a flat layer. Not only this layer reflector is flat, but also water bottom flat. But most likely water bottom is not flat. You have a dipping or curve, and here this one might also have dipping, right? So it's not necessarily identical, but in the same trend. This is the second leg of the multiples, right? So if we compare those 3 different multiples, this is basically similar to one side, right? Let's compare these 3 different multiples. One is pure water layer multiples. One is we call the pixel multiples, right? No, the third one will be another multiple, which is sub water bottom multiples, right? So which one has the smallest velocity in terms of RMS velocity? It must be water layer multiple, right? Because the water layer multiple, you have RMS velocity because they are constant, right? So 3 layers, 1 layer, 2 layers, 3 layers. Assume we have a 1 layer, 2 layer, 3 layer, but each layer has a constant velocity. RMS velocity equal to that constant velocity, right? So which is a water layer. But for the peak leg multiples, you have some part of a layer, this one, higher. You have a higher velocity than the water layer, you see that? Sub water bottom is you have velocity higher. So even from here to here, the average velocity is not exactly the same as the velocity in this layer, but still higher, right? So this velocity higher than water layer velocity, right? So this, if you consider this 2 layers, RMS of this layer velocity and this average velocity, that velocity is higher than purely the multiples at the water bottom, at the water layer, right? And then if we have the third type of velocity multiples, you have another layer in between. You have a multiple here, come back, that's even higher, right? So just see the water layer multiples, how many bands in your final multiples. So that's the 2 peak legs. Second order peak legs have a velocity higher than lower than the first order peak legs, right? Because we have twice, we have 2 apparent layers with a lower velocity. That's easy, isn't it? Yeah. Okay, that's true. I didn't show you an example of a subsurface layer multiples, but here you see, you know that at least if the sub-water bottom layer involved, the velocity higher. I showed this example before. You can see from here, horizontal from here to here, 1500, all this energy here definitely related to the water layer multiple. But we don't know exactly which one's a pure water layer multiple, which one is a peak leg multiple, which one's a first order peak leg, which one's second order peak leg, which one's a source part peak leg, which one's a receiver part peak leg, right? But nevertheless, this velocity, all these velocities, multiple related refractions have a velocity smaller than the true smaller subsurface refraction velocity. So this part of energy definitely are the multiples, although we don't know exactly the order, right? So now let's go back to what we said before. Stacking can help us to suppress the noise. The noise includes random noise. We see the random noise will be reduced by square root of n, 1 over square root of n, right? And so that means more traces in your CMP data. You have, after stacking, your signal ratio will be improved more because the noise attenuation depends on the 1 over square root of n. So n bigger, that means noise attenuated more. Right? You have only single trace, means there's 100% noise there, right? You have 2 traces, the noise will be reduced to the square root of 2. 1 over square root of 2, sorry. Right? If you have 100 traces, you're 1 over square root of 10, which is a square root of 100, which means 1 over 10. So if you have 100 traces, random noise reduced by 10, only 10% for original one, right? You see that? So more traces in your CMP data, will have a more effectiveness in the random noise attenuation. For the another part of noise is coherent noise. I just show you the example here, typical for marine data processing, water layer multiple related. So stacking can also helps you to attenuate multiples. But I'm so reluctant to say that because there are two reasons. One, this assumption here, you assume the water bottom is flat and the subsurface structure flat. But that's in reality is hardly be true. Right? That's the this is one thing. Secondly, you know the hyperbolic curve, when in the far offset you can see the larger delta t, larger NMO correction, larger NMO residual. But in the near offset, they're almost flat, almost flat. So after stacking, because the multiples is not that out of phase, right? They actually still have energy kept. So this processing. In the later stage, next session, we'll deal with that, a dedicated technology for multiple removal. Okay, that's one of our hot research topics actually in the geophysics field. Right? This sort of uses stacking as a tool to reduce the multiple, to attenuate the multiple. This is best for the deeper water, because if water layer is deeper, that means your the percentage of water layer velocity in your IMS velocity, the weight will be higher. You see that? So that means velocity lower. Okay, that's best for deeper water. As I said, near offset need a special treatment. Here we call the inner trace mute. I just show you an example how to do that. Right? Now, give you example here. That's for coherent noise attenuation. You have 3 CMP gaiters. Curve looks like this. That's pretty much this multiple. There's another multiple. You can see that. Right. For the short gaiter with dot here, if we make this layer flat, that's a stack section. This red dot is a CMP point, right? You can see the CMP gaiter here, and the green one is CMP here, blue one, CMP here. After correction, if you make this flat, your water layer, because of this velocity is higher than the water layer velocity, so water layer related to the multiple, water related to multiple, velocity lower, so the higher velocity, that means this one under-corrected. Velocity higher is under-corrected, right? Understand, yeah? And this is also under-corrected. And but for this target layer, but for the multiple in the stack section, how to recognize your multiple? That's water bottom. If you assume for 1D case, that's a 1 point, just 1 times 1 times 1. Here's 1 point like 1.3. If we multiple bounce twice in the water layer, so the second order, the first order multiple will be 2.6, right? So from here will be 2.6. And the second order will be another 1.3, will be 3.9, will be here, right? Because it's slightly not flat, slightly here. So after the NMO correction, you partially cancel this coherent noise, which is reflection multi-layer multiples, the water layer multiples. But in the near offset, you can see this is almost flat. So you still see multiples here. Right? You see there are some strong multiples here. That's not good enough, right? Now what we do? We try to inner mute, you cut off inside this bit, very like, the multiples are almost flat. You cut off this and then generate final result, right? So this is the way. We already said the number of the noise reduction controlled by fold of coverage. As I said, if you have for random noise, it's 1 over square root of a fold, right? 1 over square root of n, right? And also, of course, depends on the spatial sampling offset. Right? If you too close to each other, that means if you cancel, if you do summation, you cannot cancel that, right? But that means you neighboring traces should auto phase. If we cancel, if adding them together, you can cancel them, right? More importantly, we need a inner mute. I will do that later. The muting. So muting, we try to remove data from a stack, so 0 offset sample. Typically for mute means you just you do not use a physical scissors to cut it, right? But in the computer, you simply just zero out these samples, zero out the values, right? For we already mentioned the mute before for larger offset for the stretching factor, right? If it's stretching factor larger than a certain number, large stretching factor means the time interval after the NMO compared to the time interval before NMO. That's the ratio, stretching ratio. Now, this muting well, it's not technology, muting tool also needed for small offset. We said that this one for large offset, which is for large offset, we mute out the stretching factor, but for the small offset, we also need that. We mute the multiples. That's called the inner mute, outer mute, right? So the muting changes the fold because you mute out some values, some traces zero out. So the number effective fold, number for stacked trace actually reduce because of mute. That's the example inner mute, right? Because from this multiple, if you stack them together in the previous section, you can see they still have residual. So you do the outer mute cut from here, that's get rid of stretching factor. The inner mute here get rid of part of multiples. Right? Again, this is not the ideal one, right? So give a good stack section, but it's not the idea because if we do an NMO analysis, do AVO and amplitude variation with offset, you do need no amplitude at near offset and far offset in the comparator, right? But at least this is one way to get a good stack section. Okay, let's see the effects of stacking. For single fault, each CMP you only have single trace, you display looks like this. And if you have multiple traces in every CMP together, you can improve them. Right, you can see this provides us a much clearer image, right? That's a CMP stack. So what we learned today, first of all, a CMP concept. CMP concept is a link between acquisition and the processing, right? Of course, acquisition is for the final image. So processing is also for the final image. So CMP concept mainly try to provide redundant information. Those information help us. In this case, we at least have two usage. One, because of redundant information, because of the fault of CMP, we after stack, we improve the signal to noise ratio of your data, right? By attenuating multiples, which is a coherent noise, attenuated random noise as well, right? That's the one purposes. Secondly, is CMP provide redundant information for us to do the velocity analysis, because we don't know, we do not measure the rock samples, we don't know exact velocity. We need based on the seismic data, in this case based on CMP gathers, right? So find out the velocity. So that's the CMP concept. It's a processing concept in the house, but in the field acquisition, you must acquire the data so that you can do inside, right? It's not generated by inside. For CMP, the quality of a CMP is measured by number of channels per CMP gather. It's called a fold. So how many traces within single CMP. And the fourfold means you have an ideal number of traces within single fold, right? The property we explore is called a move out, which is a function between the offset and the travel time. The travel time function depends on the offset, right? That's called move out. The formula to represent a move out is called a hyperbolic equation. It's hyperbolic equation, okay? Move out is a hyperbolic curve. Hyperbolic curve came from the ideal situation from a model to derive a curve, which is if we have a constant model, you have hyperbolic equation, right? But for the data processing, we start from a data space, from a data, right? We do not know model, and then we can do the reverse processing, inverse processing, just from data space derive a velocity. So this velocity we call the NMO velocity. NMO velocity is not exactly as the RMS velocity. RMS velocity is mathematically derived from model. That's the difference. RMS velocity derived from model. You have a layered model, have a velocity for each layer, and then you mathematically derive RMS. But NMO velocity is data driven. It's from data. They are in a totally different space. One's model space, one data space. They cannot mix them. Although we assume they are similar, right? We got an idea from a constant velocity from the model, but in reality, we start from data, so that's totally different. So for geophysicists, we should definitely understand the physics before we understand detailed physics, but we do need to know, first thing we do need to know is the space. It's a model space or data space, right? That's the first thing. Second thing we should know is units. So remember, typically for the research student, everything you should ask is model space or data space. Second one you should ask, this equation I derived is what's the physical units for each individual variables, each individual term, right? If we have these two things solid established, and then you can go to the physical meaning, go to the next level. That's the thing. For here, I know I've done so many concepts, but if you always think about this tool, one is what's the domain, model space or data space. Secondly, what's unit, and then you can simplify the concept, simplify all the procedure here, right? That's the thing. Okay, typical for third years, fourth year student, probably this helps you to understand this geophysical concepts. Okay. Because the hyperbolic equation have a t squared, x squared, so we can have, if we assume x squared as a single variable, so you can consider the second order equation as a first order linear equation, right? So you have a t squared x squared method, and the slope, the gradient of a linear function is 1 over velocity square. So based on this analysis, you can use the pen and the pencil, either pen and the paper, you can derive the constant velocity. And the computing, in the computing software, you do have a velocity spectral analysis tools, right? Also, based on the Dix equation, you can derive, based on the stacking velocity, to derive layered velocity for individual layer. So you can see now, if you use Dix equation here, you can see that the processing steps. You from data, derive a data-driven velocity, which is stacking velocity, and based on Dix equation, you derive interval velocity. This interval velocity will be very close to the geological velocity for that layer. Geological model means model space, you see. So from data space, go gradually go to the model space. So anything you acquired from a subsurface is data space, but anything is inside the subspace or derived subspace is a model space, right? So this you can see the logical here. So this from here you see the redundant information is important for us. And in terms of processing, stacking helps us to suppress or attenuate noises, including the random noise and coherent noise, right? Coherent noise is multiples, right? The finally, as now we finish session 4, basically halfway through. We already achieved half of the first objective. However, it's not the ideal case here. We still have multiples. This leads us to the next session. Next we will how to deal with this in detail.